Hi class, how are you today? Let's see here. If there's a 0% chance that you would answer, and we've had 15 videos so far, what's the chance that you responded to at least one of them? Well, 0. Thanks for answering. The learning target for today is to be able to use binomial distributions to compute minimum values based on a needed P of R probability. The scale, 3, you can use binomial distributions to compute minimum values based on a needed P of R. 2, you can create a histogram for binomial distributions. Yes, histograms again. Don't you love them? 1, you can create a binomial distribution table. And 0, you cannot create a binomial distribution table. Let's get started. Additional properties of the binomial distribution. And those cheetahs before getting the graduation speech have now turned into humans and they're graduating. Yay! Focus points. To make histograms for binomial distributions, to compute mu and sigma, expected value and standard deviation, for a binomial distribution, and compute the minimum number of trials n needed to achieve a given probability of success, P of R. Now, this last one is very important, and you'll see it used a lot in real life and business. The kind of thing where kills 99% of bacteria. Those kinds of things come from this strategy. So that's what we're going to be working on today. Graphing a binomial distribution. Any probability distribution may be represented in graphic form. How should we graph the binomial distribution? Remember, the binomial distribution tells us the probability of R successes out of n trials. Therefore, we'll place values of R along the horizontal axis and values of P of R along the vertical axis. Kind of like when graphing a function, you graph x on the x-axis and f of x on the y-axis, the vertical axis. So x, f of x. This is the same thing here, R, P of R. The binomial distribution is a discrete probability distribution because R can assume only whole number values such as 0, 1, 2, 3, so on. Therefore, a histogram is an appropriate graph of a binomial distribution. How to graph a binomial distribution? Place the R values on the horizontal axis, place P of R values on the vertical axis, which we just talked about. Then construct a bar over each R value extending from R minus 0.5 to R plus 0.5. Again, remember back from histograms, we do that to show the range, and so we're not just cutting off right at the whole number and getting confused where that lies. There isn't actually any values between the whole numbers. We just bring the histograms like that, so there's no confusion. The height of the corresponding bar is P of R, the probability. A waiter at the Green Spot restaurant has learned from long experience that the probability that a lone diner will leave a tip is only 0.7. I would probably stop working there if that was the case. During one lunch hour, the waiter serves 6 people who are dining by themselves. Make a graph of the binomial probability distribution that shows the probabilities that 0, 1, 2, 3, 4, 5, or all 6 lone diners leave tips. This is a binomial experiment with n equals 6 trials, because there are 6 lone diners. Success is achieved when the lone diner leaves a tip, so the probability of success is 0.7 and that of a failure is 0.3. So n is 6, p is 0.7, and q is 0.3. We want to make a histogram showing the probability of R successes when R equals 0, 1, 2, 3, 4, 5, or 6. It is easier to make a histogram if we first make a table of R values and the corresponding P of R values. So if you see here, for each R value, we've calculated what the P of R will be. Remember how to do that? We learned that last time. So for each R value, we get a P of R value. So this is a table that I mentioned to be able to give this is a 1. We'll use table 3 of appendix 2 to find the P of R values for n equals 6 and P equals 0.7. To construct the histogram, we'll put R values on the horizontal axis and P of R values on the vertical axis. Our bars will be 1 unit wide and will be centered over the appropriate R value. The height of the bar over a particular R value tells the probability of that R. The probability of a particular value of R is given not only by the height of the bar over that R value, but also by the area of the bar. Each bar is only 1 unit wide, so its area, which is height times width, is equal to its height, because the width in this case is 1. However, in some cases, you can, if there's a lot of R values, you can spread them out, and the probabilities would be based on different widths. But it's much easier to deal with width of 1, so you're not getting confused. Since the area of each bar represents the probability of the R value under it, the sum of the areas of the bars must be 1. In this example, the sum turns out to be 1.001. It is not exactly equal to 1 because of rounding error. So that's what rounding does. It can make errors. It is equal to 1, but because of the rounding, it just doesn't look like it. Mean and standard deviation of a binomial distribution. How to compute mu and sigma for a binomial distribution. Mu is NP, the expected number of successes for the random variable R. Sigma is the square root of NPQ, the standard deviation for the random variable R. Remember that R is the random variable representing the number of successes in a binomial distribution. N is the number of trials. P is the probability of success on a single trial. I teach geometry too. Triangles show up. And Q equals 1 minus P, the probability of failure on a single trial. Remember, 1 minus P is the complement rule. So it's actually pretty easy for binomial distributions to be able to find mu and sigma. Mu is just n times P, and sigma is the square root of n times P times Q. Let's compute the mean and standard deviation for the distribution of example 7 that describes the probabilities of lone diners leaving tips at the Green Spot restaurant. In example 7, we had n equals 6, p equals 0.7, and q equals 0.3. For the binomial distribution, mu will be n times p, so 6 times 0.7, which is 4.2. The balance point of the distribution is at mu, 4.2. The standard deviation is given by the square root of npq, which is square root of 6 times 0.7 times 0.3, which is the square root of 1.26, which is approximately equal to 1.12. Quota problems, minimum number of trials for a given probability. In applications, you do not want to confuse the expected value of R with certain probabilities associated with R. Quotas occur in many aspects of everyday life. The manager of a sales team gives every member of the team a weekly sales quota. In some districts, police have a monthly quota for the number of traffic tickets issued. I don't want to live in those districts. Nonprofit organizations have recruitment quotas for donations or new volunteers. As much as you probably don't like these things, they are how businesses work well. The basic ideas used to compute quotas also can be used in medical science. How frequently checkups should occur, quality control, how many production flaws should be expected, or risk management, how many bad loans a bank should expect in a certain investment group. To have adequate power, a satellite must have a quota of 3 working solar cells. Such problems from many different sources, but they all have one thing in common. They are solved using the binomial probability distribution. To solve quota problems, it is often helpful to use equivalent formulas for expressing binomial probabilities. These formulas involve the complement rule and the fact that binomial events are independent. Equivalent probabilities will be used in example 9. How to express binomial probabilities using equivalent formulas. So the probability of at least one success is P of r is greater than or equal to 1, so 1 minus P of 0. 2 successes, 1 minus P of 0 minus P of 1. 3 successes, 1 minus P of 0, 1 minus P of 1, minus 1 minus P of 0, minus P of 1, minus P of 2. So the probability of at least m successes is 1 minus P of 0, minus P of 1, minus all the way on until you get 1 less than whatever m is. So you just subtract out the probabilities of failure, effectively. Junk bonds can be profitable, as well as risky. Why are investors willing to consider junk bonds? Suppose you can buy junk bonds at a tremendous discount. You try to choose good companies with a good product. The company should have done well for some reason, but for some reason did not. Suppose you consider only companies with a 35% estimated risk of default, and your financial investment goal requires 4 bonds to be good bonds in the sense that they will not default before a certain date. Remember, junk bonds that do not default are usually very profitable because they carry a very high rate of return. The other bonds in your investment group can default, or not, without harming your investment plan. So what we're doing here is getting to a spot where you would be comfortable with the bonds you're getting, and even if the bonds do better than you hope, that's great, but there's a high chance, to whatever probability you set it to, that your bonds will not go below a certain point. So for this percentage, let's say, suppose you want to be 95% certain of meeting your goal of at least 4 good bonds. How many junk bond issues should you buy to meet this goal? Since the probability of default is 35%, that's a bad thing, the probability of a good bond is 65%. Let success S be represented by a good bond. Let N be the number of bonds purchased, and let R be the number of good bonds in this group. We want the probability that R is greater than or equal to 4 be greater than or equal to 0.95. So we want to, when we calculate the probability that R is greater than or equal to 4, we want that probability to be greater than or equal to 0.95, greater than 95%. So this is equivalent to 1 minus P of 0 minus P of 1 minus P of 2 minus P of 3 is greater than or equal to 0.95 because we're taking out the failures, the probability of failures, or not getting enough failures in this case. So since the probability of success is P equals P of S equals 0.65, we need to look in the binomial table under P equals 0.65 and different values of N to find the smallest value of N that will satisfy the preceding relation. So we look under the table and look at different values of N to be able to get to the probability that we're looking for. In Table 3 of Appendix 2 of your book, shows that if n equals 10 when p equals 0.65, then 1 minus p of 0 minus p of 1 minus p of 2 minus p of 3 is equal to 1 minus 0 minus 0, because they're too small to round to 3 decimal places, minus 0.004 minus 0.021 will give us 0.975. So 97.5%. The probability 0.975 satisfies the condition of being greater than or equal to 0.95. We see that 10 is the smallest value of n, which the condition p of r is greater than or equal to 4 is greater than or equal to 0.95 is satisfied. Under the given conditions, a good discount on price, no more than 35% chance of default, and a fundamentally good company, you can be 95% sure of meeting your investment goal with n equals 10. Carefully selected junk bond issues. In this example, we see that by carefully selecting junk bonds, there is a high probability of getting some good bonds that will produce a real profit. So this is the kind of thing that statisticians love. You look at a real world problem, in the real world, you look at a problem and people think common sense, you don't want to go for these quote-unquote junk bonds because they're bad. But you can statistically calculate how you'll come out on top even going for what seems like a bad idea. Now time for the sponge. Jim enjoys playing basketball. He figures that he makes about 50% of the field goals, that's baskets that aren't three-pointers, he attempts during a game. Make a histogram showing the probability that Jim will make 0, 1, 2, 3, 4, 5, or 6 shots out of 6 attempted field goals. And the second question. A satellite is powered by 3 solar cells. The probability that any one of these cells will fail is 0.15, and the cells operate or fail independently. What is the smallest number of cells the satellite should have? What is the smallest number of cells the satellite should have to be 97% sure that there will be adequate power? That is, that at least 3 of the cells will work. So, what's the smallest number of cells that they need to be 97% sure that at least 3 of the cells will work? That's it for the lesson. Once again, please make sure to take notes on the entire lesson. Don't forget to rank yourself back from the learning target so I know what you are. Take a picture or a video, I prefer picture, of everything, submit it all to Google Classroom, and have a good night.